Hello everyone, we're Jiahao and Yangfei. Today we'll be presenting our work on 3D orientation estimation for symmetric objects using augmented autoencoder. Orientation estimation from RGB refers to the process of determining an object's orientation using color images captured by a camera. It has various applications in computer vision, robotics, and augmented reality. For instance, the estimated orientation could guide robots to perform subsequent tasks, such as object manipulation and grasping. However, pose ambiguity caused by symmetries and occlusion could pose a big challenge to such a method because RGB images only have limited information about an object's 3D structure. In 2020, Meyer proposed the augmented autoencoder, and supervised learning approach that incorporates additional information to enhance the quality of the learned pose representation from RGB images. Our project aims to investigate the effectiveness of AEE in handling symmetric object and occlusion cases. There are two crucial steps to predicting orientation from RGB images using AAE, which are image reconstruction and template matching through pre-computed codebook. The image reconstruction process of AAE involves first feeding images with noise into the encoder and the decoder network, which generates a reconstructed image that should match the original image as closely as possible. In previous step, we could get a codebook of latent vectors, where each vector corresponds to a unique orientation. In prediction process, a cropped image around the object's center will be fed into a trained AAE and obtain a query latent vector. We then computed the cosine similarity between the query latent vector and the vectors in the codebook. Eventually, the highest similarity determines the predicted orientation of the object. We have chosen some reflection symmetry and rotation symmetry objects from TLAS dataset. We will conduct experiments to evaluate the performance of AAE on these objects and also try to explore potential improvements on current AAE implementation. Training process only requires CAD models and background images. Then the rendering engine will synthesize training images with some data augmentation techniques during the training process. Augmentation includes random lighting conditions, random occlusion, padding, and saturation. We determined our common training set for each object based on preliminary experiments. Some key settings and hyperparameters are listed in left-hand table. The pictures on the right hand are some intermediate results during training process, which are training input images, output of AAE, and rendered ground truth respectively. We evaluate the trained AAE model on a test set of 50 real images. In this figure, each group of 3 images represents the input real images, the ground truth, and the AAE model prediction, respectively. Intuitively, the majority of the predictions in the figure are similar to their ground truth. However, observation based on eyes doesn't provide an accurate evaluation of the model's performance. Therefore, we still need quantitative evaluation to have a better understanding of the model's performance. This table shows model performance for each object. The first 3 matrices presents pixel-wise precision for each object's pose reconstructed by a trained AAE. We also added matrices to measure the angle error of the predicted orientation along the x, y, and z axes respectively. While our results showed visually accurate predictions for most objects, we observed larger errors in raw and yaw angles. Our suspicion is the pose ambiguity is caused by rotational symmetry. To address this issue and makes the model more robust, we had some trials such as using different background source to increase the variation in training set, or add some occlusion to training data. However, our attempts didn't lead to significant improvements. In fact, some matrices even decreased. In conclusion, we re-implemented augmented autoencoder trained on TLS objects, and then evaluated the performance of AAE using different matrices and found its limitation of handling symmetric objects and occlusion cases. For future direction, existing research suggests replacing the average pixel difference loss with other feature losses. So investigating the effect of image fidelity is a potential direction to reason about the results of this project. Thanks for watching.